All right, we're recording. Go ahead.
Welcome, everyone. We're happy to have Jeremy Booher from the University of Canterbury here today to talk about, can you hear the shape of a curve?
Hi, thank you all. So, can you? What do I mean by a curve? Maybe is the first thing to talk about. I'm thinking of an algebraic curve. So maybe an equation like a polynomial in two variables. And I'm looking for the solutions to that. And if I look over the real numbers, I might get a picture like this, where it really looks like a plane curve. If I look at complex solutions, I get a Riemann surface, for example, like this one. This perspective makes certain properties of the curve more clear. For example, the curve I've drawn here has genus 2, and you can really see the two holes. And that's not something that's so apparent from just looking at the real points. Now, the focus of today's talk is really looking at curves over finite fields. So for example, I can look for solutions where the variables are integers modulo a prime p. And there, I get a finite set of points. It's not so clear how to do geometry, although you can. But it also allows you to do new things that are interesting to number theorists. For example, you can count the number of solutions. So this first part of my talk is going to be sort of a warm-up problem, sort of introducing what algebraic curves are and what you can do with point counting. Then in the middle, I should probably tell you what the title of my talk means. It's related to the classic question, can you hear the shape of a drum? And it'll involve talking about what covers of curves are. And then towards the end, I'll start talking about some results, heuristics, and future directions. Sort of just to summarize ahead of time, the idea is, how can we hear the shape of a curve by using the zeta function of covers of the curve to distinguish the curve? So let's start with this warm-up. It's about elliptic curves, which are a really nice example of curves. And so I might specify them by saying y squared equals a cubic polynomial in x. Here are a couple of examples. And what I've done is I've counted the number of points on the curve, the number of solutions to these equations, basically. And I've done this modulo p for various small primes p. And as you'll note, occasionally they'll have the same number of points mod p. Most of the time they don't. And so a very natural question is, how often does this happen? How often do E1 and E2, these two elliptic curves, have the same number of points on them modulo p? And so the set of heuristic you should have in the absence of additional information is the number of points, which we write this way to indicate what field we're using. This should be random. And it should be random from around a constant times the square root of p choices. So in particular, if you believe this heuristic, that says that these two elliptic curves should have the same number of points on them with probability roughly 1 over a constant times the square root of p. So it'll happen, you'd expect, for infinitely many primes, but it won't happen too often. And so where does this heuristic come from? And it really comes from thinking about the elliptic curve geometrically, not just trying to solve an equation, but trying to sort of understand it geometrically. And so therefore, I should tell you, what is an elliptic curve? Well, over the complex numbers, it's a Riemann surface of genus 1. A torus. And you should think of it as the complex numbers modulo a lattice. Now, I am aware not everyone may be really familiar with what a lattice is, so let's just look at an example. I've drawn a picture here of the standard lattice. It's the red points in the complex plane, and it's the points where the real and imaginary part are integers. And so when I take C modulo a lattice, what I'm doing is I'm saying, well, all of those red points are supposed to be glued together. And furthermore, 2 points that differ by one of these red points, one of these points in the lattice, are also the same. So because I'm not able to add integers in I times integers, I end up getting a fundamental domain, which is just a square side length 1. And adding 1 will glue the left and right sides, and adding I will glue the top and bottom. And so topologically then, you glue these together and you see you get a torus. And so that's sort of explaining why elliptic curves are genus 1. Now, we also would like to look over the real numbers. This is a nice picture because it actually looks like a curve. On the other hand, it's not so clear how to some other features. So one other feature is that you can add. You can add complex numbers, and so you can also add points on an elliptic curve if you have a group law. It's really useful. But it's not so clear what that should do here. It's definitely not just like taking points and adding up the coordinates. In fact, it turns out if you take a line and you find the 3 points of intersection with your curve, those 3 points add up to 0. And if you sort of unwind this, it means that the sum of P and Q is this point down here you get when you reflect R over the x-axis. Now, I really want to look over finite fields because I'm an arithmetic geometer. So over finite fields, well, you don't have a picture. It's not so clear what the group law is until you start using algebraic geometry. And that lets you make sense of all these geometric notions in this setting as well. And then you do, and it's really nice. You get a group law. You understand what it means to be genus 1. And in particular, then you can say something about the number of points on the curve based on this geometry. This is the Hasse-Weil bound. And roughly, it says that the number of points on the curve is around p plus 1. If you sort of look at that difference, take the absolute value, it's bounded by 2 times the square root of p. And this is really a consequence of sort of geometric facts, and in particular, the exact bound I get depends on the fact that I have a genus 1 curve. And so this bound is explaining the sort of heuristic I mentioned earlier. If we go back and look, when do these curves have the same number of points on them mod p? Well, our heuristic is that the number of points on each of them is going to be sort of random, but it's going to be subject to the Weil bounds. And there are a few other constraints that aren't going to matter. So because of the Weil bounds, this tells us the chance that the 2 elliptic curves that I've picked have the same number of points mod p, that's going to be a constant over the square root of p, just based on the number of choices given to you by the Weil bound. So this is sort of the default. In the absence of additional information, this is what you should assume. Of course, you can fail miserably. Here's an example. I've looked at a 3rd elliptic curve. I've counted the number of points on them modulo p, and I'm always getting the same number. So your first reaction is, well, maybe I just sort of made some change of variables, and the 3rd elliptic curve is really the same as the first one. That's not what happened. They're really different elliptic curves, but of course there is some relation between them. The relationship is they're isogynous. So this is something that I'll just briefly mention now, and it's going to sort of be sort of lurking in the rest of the talk. It's a very useful perspective in actually proving things, but I'm going to sort of hide it for most of the talk. But very briefly speaking, it's saying there's a map from E1 to E3 that is both a map of algebraic curves, and it's also a group homomorphism. Anyway, so all you should think about really is that there's some geometric reason why these curves have the same number of points, and we don't need to really focus on exactly what it is. All right. So today I really want to look at higher genus curves. They're sort of more complicated. And to sort of connect the point counting with that, we really want to look at things slightly differently. We want to look at the zeta function of a curve. So what is a zeta function? Well, if I have a nice curve over a finite field, I can define the zeta function in one of 2 ways. The first way is as an Euler product. This means I take a product over each of the points of the curve, and there's some contribution from that point. Exactly what it is actually a little technical to define because it involves thinking about X as a scheme. So probably, if you don't know that, you should focus on the second one, which just involves point counting. The idea is look at the number of points in your curve over the field FP, but also over all of its finite extensions. Count them, and then put them together to make a generating function. So this is called a zeta function, and it's called this because it's sort of analogous to the Riemann zeta function, which is a very famous function that people encounter in analytic number theory. Is a product over prime numbers in the integers, and it has some contribution from each prime. And as you might expect, it tells you things about primes. In particular, you can study it to prove the prime number theorem. And it sort of superficially looks similar to the zeta function of a curve. If you generalize it a bit, you can also look at a Dedekind zeta function of a number field. So that's a finite extension of the rational numbers. So maybe it's the rational numbers, q adjoint square root of d, or other number fields. And there, the Dedekind zeta function is also a product over prime ideals in the ring of integers of your number field. And then there's some local contribution from each one. Now, this is starting to look really similar. Instead of a product over points of the curve, you have a product over prime ideals of a number field. And one thing that you might know if you've learned some algebraic geometry is that you should really think of prime ideals as being points. And so these are looking really similar. And in fact, you can fit them into the same framework. So just as the Riemann zeta function and Dedekind zeta function tell you about primes, the zeta function of a curve tells you about the points on the curve. So let's try to see an example of this. Let's look at an elliptic curve again. And the zeta function will depend on the number of points in that curve over fp. In particular, the zeta function is going to be a rational function, has a simple denominator that doesn't depend on the curve, but the numerator does. Depends on the point counts to this quantity a of e, and then you end up with quadratic polynomial on top. So on the one hand, this is really simple. The zeta function just depends on the number of points on the elliptic curve over fp. Doesn't actually depend on looking at all the extensions of fp. On the other hand, it should be really surprising that the answer is so simple. I mean, you formed this power series generating function, you took the exponential of it, and then suddenly you get a really simple rational function. And this is surprising at first, and it's really connected up with ways to compute the zeta function using geometry. I don't want to fully say how to do this, but because this sort of a broad outline will be useful later for motivation, I want to say just what you would do very briefly. And the idea is you look at something called the Frobenius, which is a map from an elliptic curve to itself. And what you do is you take a point on the curve and you raise both the coordinates to the pth power. This gives you a map from the elliptic curve to itself, and therefore it induces endomorphisms of various vector spaces that are associated to the curve. You can think of these as the cohomology of the curve, or sort of more down-to-earth versions of that. And so in particular, if you want to compute the zeta function of the elliptic curve, what you do is you think about sort of what the Frobenius does to one of these vector spaces. In particular, you really want to understand the eigenvalues of the Frobenius. In particular, the numerator of the zeta function turns out to be the reversed characteristic polynomial of the Frobenius operator. Right. So the thing to take away from this is I really want to look at the eigenvalues of Frobenius to compute a zeta function. Now, I was interested in looking at higher genus curves. So for elliptic curves, there are a bunch of equivalent things. One is just having the same number of points on the elliptic curve over fp. That's equivalent, as we just saw, to having the same zeta function. And that's equivalent to the Frobenius eigenvalues being the same. And then the following is not so obvious, but it's a famous result of Tate, that that's equivalent to the elliptic curves being isogynous. So if you think back to that example where we had two different elliptic curves that always had the same number of points in them mod p, that was because they were isogynous over the rational numbers, and hence isogynous over almost every finite field. That meant they were isogynous, so they have the same zeta function, and they had the same point counts. Now, for higher genus curves, the second perspective, looking at zeta functions, is really the way to go. You don't want to just look at the number of points on the curve. You'd have to really look at points over extensions as well. So it's better just to focus on the zeta function. And you can sort of reformulate this in terms of Frobenius eigenvalues and geometrically, but that's not something I'm going to focus on. If you know what a Jacobian is, here's an equivalent condition in red, but I don't expect you to know that. So as I said, in this talk, I really want to look at higher genus curves, and I want to focus on curves that have the same zeta function. And when does that happen and how often? Before I do that, though, I want to sort of put in a little historic interlude about number fields for the same zeta function. This was studied in the early 20th century, and Gossman came up with a nice way to produce examples. His idea was, suppose you have a finite group G, and you have two subgroups that sort of look the same to conjugacy classes. In other words, for every conjugacy class of your group, if you take the size of the intersection of that conjugacy class with these two subgroups H1 and H2, they always have the same size. So those are subgroups which look the same in this manner. Now, we're going to say this is called a Gossman triple, and we'll say it's non-trivial if H1 and H2 are not conjugate. Just sort of taking one subgroup and conjugating it is a cheap and sort of boring way to produce a Gossman triple. But let's try to be more ambitious and find something that's actually sort of interesting. So there's an example with a symmetric group over here. This is S6, and I have two subgroups. And Gossman's idea was, well, suppose I take an S6 extension of the rational numbers. In other words, a Galois extension whose Galois group is S6. If I take the fixed fields of this with respect to H1 and H2, I get two number fields. Turns out they have the same zeta function, and they're not isomorphic. And this is precisely because we had a non-trivial Gossman triple. So this gives a very sort of nice construction, a number of fields with the same zeta function. What about for curves? Well, now I think it's really time to explain the title of my talk. So the title was, Can you hear the shape of a curve? And this is really a sort of family of questions, the most famous of which was, can you hear the shape of a drum? So this was popularized by Kak in the 1960s. And the idea is, suppose I have a drum, think of it as a region in the plane. I hit it, it vibrates, it makes a noise. Can I tell the shape of the drum from what I hear? Mathematically, how a drum vibrates is controlled by the spectrum of a differential operator called the Laplacian. And so the question is, if you know the spectrum of the Laplacian on a domain in the plane, say, does that tell you the region, the shape of the region? So very quickly after this question was sort of popularized, people came up with complicated higher dimensional examples where you can't. In other words, there are regions, there are more complex, higher dimensional regions that have the same spectrum of the Laplacian, but they have different shapes. But it wasn't for a lot later until people knew the answer for regions in the plane. So Tsunada realized that this is connected to Gossman triples, which were about zeta functions of number fields. And using this connection, Gordon, Webb, and Walpert in the 1990s were able to produce examples of regions in the plane that have the same, that sound the same, have the same spectrum of the Laplacian, and they have different shapes. Here's an example, these two regions. So the answer is no, you can't hear the shape of a drum. Of course, it does tell you a lot of information, so not everything is lost. Now, the question I want to focus on today is, can you hear the shape of a curve? By that, I mean a curve over a finite field. I've given you a picture of a curve over the real numbers, but really we should work over a finite field. And what do we look at? Well, we look at the zeta function of the curve. That's what tells you about all the point counts. But we think about computing it by looking at the spectrum of the Frobenius. So that's sort of it's a natural linear transformation, and we're looking at its eigenvalues, exactly analogous to the way you look at the spectrum of the Laplacian. So can you hear the shape of a curve directly? The answer is no. We had an example earlier where we had two isogynous elliptic curves. They always had the same number of points in the mod p, therefore they had the same zeta function and the same spectrum of Frobenius. And then there's an analogous question for number fields. Of course, this is, can you hear the shape of a number field? Maybe your number field is q adjoint a square root of d, for example. You look at the Dedekind zeta function, and as Gaussman showed, no, you can't. Of course, the number fields are still similar, but they're not definitely the same. So this is a really pretty connection. We're seeing these ideas sort of percolate from one area of math to another area. There's these exciting connections between different areas when you phrase the question this way. And people have also looked at other versions of this that I'm not going to focus on. There's a version for graphs. Can you hear the shape of a graph? This is a question about isospectral graphs. There's also, of course, interest in the version for higher dimensional drums, which are talking about isospectral Riemannian manifolds. Anyway, so it's sort of a bummer that the answer to all these questions is no. But not all hope is lost. And the reason is, if I just give you, for example, a curve over a finite field, there are lots of other natural curves that sort of map to it. And there are ways to construct these in sort of reasonable ways. And there's sort of algebraic analogs to covering spaces. And it's a very useful idea in topology to, study covers. And so maybe we should do the same. In particular, if I look at the zeta function of a curve C and a zeta function of C prime, knowing that they have the same zeta function probably doesn't tell you the curves are the same. So maybe I should construct some natural covers for both of them and say, well, suppose I tell you that the zeta functions of the covers are also the same. Is that enough information to figure out that the curves are isomorphic? If not, maybe I should just start using more covers. And so that's what I mean today by can you hear the shape of a curve? Can the zeta functions of the curve plus natural covers tell you enough information to figure out what curve you're working with? Now, once you've formulated this question, there are a huge number of natural variants. The first one is, which covers should you use? After all, not all covers are created equal. Some are probably more natural to work with, some are harder to work with. Which ones should you use? Another idea is, well, if you have a cover, it turns out if you take the zeta function of the cover, it breaks up into pieces called L functions. Maybe it'd be better to work with those pieces as opposed to the whole thing. If this problem seems too hard, instead of trying to work with all curves, maybe you should work with curves from particular families. Maybe it'll be easier to hear the shape of curves in a family, just restrict to that family, and not try to consider all possible curves at once. And then if you're ambitious, you can try to do this in a computationally efficient way. In particular, maybe you can get an efficient algorithm which can take a curve, look at some covers, compute their zeta functions, and use it to distinguish curves. Right, so I think this is a good point to sort of pause and talk about the sort of high-level motivation. So one motivation is what I told you, this analogy with the question, can you hear the shape of a drum? Another motivation is sort of comes from looking at the general question, how much information do covers give you? So Grothendieck, a very famous algebraic geometer, sort of started this program which is called Abelian geometry. And the idea is you have some object of geometric interest, and you look at covers and try to use the covers or information about them to tell you everything you want to know about the object itself. And so this is a prime example of Abelian geometry. We're taking covers of a curve, we're looking at their zeta functions, and we're asking how much information do zeta functions give? How much information does this point counting give us? A much more down-to-earth motivation is this would also be relevant for factoring polynomials over finite fields. So this is a very fundamental problem if you're a computational number theorist or doing computational algebra. And they're good solutions. In particular, there are perfectly nice randomized algorithms which will factor polynomials for you over a finite field, and they'll do it relatively efficiently. This is relevant for finding a deterministic algorithm. So if you ever do anything related to computer science and algorithms, you'll quickly realize that using randomness is a really powerful tool for solving problems and developing algorithms. However, there's this sort of feeling people have that randomness really shouldn't be necessary. In particular, no one's really sure if you really need randomness to do anything. But oftentimes it's much easier to come up with a randomized algorithm as opposed to a deterministic one. So there's a famous example of this where in the 1970s, people came up with the Miller-Rabin primality test, which could tell you whether an integer is prime. It's a randomized algorithm, so it's almost always right. It wasn't until the early 2000s that people actually came up with an efficient algorithm to deterministically, in other words, always be right, tell you whether an integer was prime. And so this question about polynomials is analogous to that. We have a good randomized algorithm. Now we're looking, can we actually de-randomize it and get a deterministic one? And so very briefly, you can do this by looking at zeta functions. There's an idea of Kayal and Poonen that you want to find a family of curves over a finite field where every member of this family has a different zeta function. If you can do this, what you should try to do is, instead of using a finite field as your coefficients, try to use fp adjoint x modulo the polynomial you want to factor, and pretend that's your coefficients. Then you should go along and try to compute the zeta function using standard methods. This will have the effect of computing the zeta function of multiple members of the family at once. At some point, because every zeta function in this family is different, this algorithm is going to fail because it won't be able to get an answer because there are different answers for each member of the family. And that failure will reveal a factorization for your polynomial. So to do this, we have to really understand the question, can you hear the shape of a curve? And in particular, we'd have to work with a family of curves that we can actually compute with efficiently. All right, so I said we should use covers of curves. Let me tell you a little more about what they are and which covers I want to focus on today. So what is a cover of curves? Well, topologically, you'd think of a cover of curves as a branched cover. And here's a picture. I can take a plane curve and project it onto the x-axis. I sort of send a pair xy on the curve to just the x-coordinate. And this is basically a 2-to-1 map. If I tell you what x is, you know what y squared is supposed to be, and then you solve. Now, you might get worried if you're trying to solve y squared equals a negative number, but you just use complex numbers and it all works out. So this is sort of a degree 2 map, it's 2-to-1, except when you're trying to solve y squared equals 0. Those are the points I've marked in red. They're called points of ramification. And they're what causes it not to be quite a covering space, but to be a branched cover. The nicest covers don't have any ramified points, and they're called unramified, and they're really the algebraic version of a covering space from topology. And so today I want to focus on 2 different covers that are really nice. The first one I'm going to call the 2 cover. There's a more precise definition down in red if you know geometric class field theory, but you should think of the 2 covers being sort of small. It's an unramified cover whose degree is a power of 2. The other one I'll focus on is called the Hilbert cover, and I'll denote h of c, and you should think of it as a relatively large cover. It's a maximal unramified cover in some precise sense. All right. So these are the 2 covers I want to focus on. I'll talk about the Hilbert cover first. This is joint work with Philippe Volek. And the idea is the Hilbert cover is quite big. So we're going to be optimistic and say maybe the zeta function of the Hilbert cover is going to give us enough additional information to hear the shape of a curve. So the first thing you have to do then is compute the zeta function. And so it turns out the zeta function breaks up into a bunch of pieces. These are called L functions. And there's one L function for each character of the group of automorphisms of the cover. There's a precise definition of what these L functions are over there. But all that really matters is we take the zeta function and break it up into simpler pieces. And the question is, do these pieces, these L functions, determine the curve? Before I answer the question, I should just want to talk about why it's reasonable to ask this. And the reason is, well, Mochizuki and Tamagawa proved a foundational result in anabelian geometry, which says if you have a hyperbolic curve over a finite field, so this, for example, could be a projective curve of genus at least 2, then the étale fundamental group of X determines the curve X. So this étale fundamental group is some version of the topological fundamental group. It tells you basically about all the covers of X. And so since the Hilbert cover is sort of a maximal cover in some precise sense, it's not so outlandish that information about the Hilbert cover would be enough to tell you about your original curve. So Felipe Volek and I can actually prove something along these lines. Suppose I have a smooth projective curve of genus at least 2 over a finite field. Then L functions for the Hilbert covers basically determine the curve up to isomorphism. The only sort of detail is you can't just look at the curve over your ground field. You have to also look at the curve where you use larger finite fields as the coefficients. But if you tell me all those L functions, I can tell you what the curve is. So this is a really nice result. The way I've stated it, it sort of hides one detail, which is it requires a way to identify the groups of automorphisms for the Hilbert covers of C and for C prime. If you don't have this, there's no way to identify the characters and therefore match up the L functions. Because if I don't tell you this, you don't know like which L functions are supposed to be matched up and then ask, are they equal? So once you have this, then you identify characters, you know which L functions to set equal to each other, and that's enough to tell you what C is. So let me say one thing now about how to prove this. So the first idea is to reformulate things in terms of the points on the Jacobian of C and of C prime. You end up getting isomorphisms between the points of those Jacobians. And then you ask, well, this is a group isomorphism. Is it induced by an isomorphism of the underlying algebraic curves? And the way to check that uses a result of Zilber. What's sort of surprising is this result is proven using model theory, using mathematical ideas from mathematical logic, and it gives us a way to approach this problem and use the information about L functions to check hypotheses. All right, so this is a nice theorem. It answers a version of our question. It has another nice corollary. We can actually recover the projective case of this result I mentioned of Mochizuki and Tamagawa, which was about the étale fundamental group of a curve determining the curve. This is a really different proof of that result, and it's sort of surprising in that it works backwards. Tamagawa originally proved that result for affine curves, and then Mochizuki leveraged that result plus a lot of other things to prove it for projective curves. Here, we get it for projective curves directly. And then, in fact, you can use standard arguments to deduce the affine case. So that's great. Does this help with the application to factoring? And the answer is not really. While we do have a family of curves that have different zeta functions, you can also use these L functions in place of that. It doesn't actually help because these Hilbert covers are just too big to compute with efficiently. You could factor a polynomial this way, but it wouldn't be any better than just using brute force. So really what we should do then is maybe look at smaller covers. And that's something that I've looked at with a group that started at an ISOM workshop. This is joint work with Vishala Rule, Stephen Groen, Everett Howe, Wanlin Lee, Vlad Matai, Rachel Priest, and Caleb Springer. It was at this ISOM workshop, which was supposed to be in person in the summer of 2020, and Instead, I spent a long time staring at a Zoom window working on this project with them. So here we have my rendition of a Zoom window inside a Zoom window. And the question was, let's look at these smaller covers. Maybe their data functions have less information. So instead of trying to work with all curves, because we have less information, let's try to work with particular families of curves. And maybe we can find families of curves where we can use covers to sort of hear the shape of a curve. So what should we expect about data functions in families? Well, if I have a family of curves over a finite field, there's some parameter I can change to vary the family, so there'll be around p curves in the family. And then if I look at the zeta function of the curve and the zeta function of some cover, say the 2 cover I mentioned earlier, there'll be some constrained set of choices for what the zeta functions can be. And so if the genus of the curve is sufficiently small, the set of possible choices is small enough that we'll expect to see a match. Although there are many more choices than there are curves, a version of the birthday paradox will tell you we'd expect some of them to match up anyway, just by chance. And so we would see curves where the zeta functions of the curve and the covers are the same. On the other hand, once the genus is sufficiently big, we don't expect them to match, just because there are way too many choices for the zeta functions. And so the goal of this project was to sort of test heuristics for specific families of curves. We have some guesses. Are they right? In particular, what are the exact constraints?
Wouldn't this be enough for 2 bottles?
Sorry. Is someone trying to ask a question? Okay, probably it was background noise then. So we're trying to test these heuristics, figure out what the exact constraints are, and then based on those heuristics, make a prediction about how many times we'll see collisions. And then it's a computational number theory question to actually count the number of collisions and see if we're right. And the motivation is to provide insight for its application to factoring polynomials over finite fields. So the specific question we focused on was, here's a family of genus 2 curves. I have this parameter S I can change. S can be something in FP. And then I'm going to look at these curves and also their 2 covers. Turns out the 2 cover has genus 17 in this case. So it's bigger, but it's still a fixed size. This is the family of genus 2 curves where the automorphism group is pretty big. It contains a dihedral group of order 8. So what we need to do is we need to compute the zeta functions of both the curve and the 2 cover. That's something that's actually easier to do by thinking geometrically using the perspectives I've sort of been hiding. So let me just tell you the answer. The zeta function of the curve turns out to be the square of the zeta function of an elliptic curve. That depends on the parameter S, of course. And the zeta function of the cover, well, it has a contribution from the zeta function of the base, and then it also has 15 other zeta functions of elliptic curves. All of these curves could depend on the parameter S. And so I'm going to say that 2 curves in this family are doubly isogynous if they have the same zeta function. And furthermore, the covers have the same zeta function. So if there weren't any doubly isogynous curves, we could really hear the shape of the curve. However, this family is small enough that we do expect to find doubly isogynous pairs of curves. And so the question really is, how often does this happen? And does it match up with our sort of predictions? So we need to make a prediction first. So let's think about this. We have these zeta functions. It turns out it's a little more complicated than I let on. The zeta function for the cover is made up out of all of these zeta functions of elliptic curves, but there are actually only 5 elliptic curves which show up there, which both depend on the parameter S and are actually there. So some elliptic curves show up multiple times, and some of them don't depend on the parameter. So they're the same everywhere in the family. So if I want to be doubly isogynous, that means, first of all, I need to have the same zeta function. And that means that this elliptic curve, these two elliptic curves have to have the same zeta function. That's the problem we talked about at the beginning and warmed up with. The chance that happens, barring any sort of special reason, we expect it to sort of to happen roughly a constant over the square root of p. That's the probability. So not too often, but sometimes. If we want to get the zeta functions of the covers to also be the same, we need to get more elliptic curves with the same zeta function. There are sort of 5 of these, and we need them all to sort of be equal by chance. Each one has chance about a constant over the square root of p. So there are p squared pairs of curves. If all of these sort of different zeta functions being equal are actually random, as we're sort of guessing, and independent from each other, we would need 6 coincidences to happen with the probability a constant over the square root of p. So the total number of doubly isogynous pairs we'd expect is some other constant over p. All right, so we've made a prediction. Now we can do computational number theory and see if we're right. So we expected a constant over p doubly isogynous pairs. So for any given prime, we may not see any, but if we look at a bunch of primes at once, we do expect to see some. So what we did was we looked for doubly isogynous pairs in our family for 1,024 primes, which were closest to 2 to the n. We did this for various values of n. And I've written it down very nicely in this chart, just so you don't think it's too easy. Some of the larger values of n took about a week of CPU time. And so our prediction was, well, we have a constant over p doubly isogynous pairs. So for primes which are around 2 to the n, the primes are all roughly the same size. And if we increase n by 1, we would double the size of the prime. So we should be having the number of doubly isogynous pairs. Is that what we see? No. It really looks like if I increase n by 2, I have the number of doubly isogynous pairs. In other words, it looks like a constant over the square root of p doubly isogynous pairs. So we were wrong. So then the question is, were we like just completely wrong in our heuristic, or is there something more complicated going on that we didn't account for? Well, then you go back and think more about these covers and this kind of geometry of the covers, and eventually you figure out what's going on. So remember, these covers had zeta functions which were built out of 6 different elliptic curves which depended on s, and then they were showing up multiple times. So you can try to look for when do these different elliptic curves that show up, when do they have the same zeta function? And you do that by looking for when they're isogynous. In red, if you know about modular polynomials, there's a sort of precise way to do this, but you do it. And when you do it, you get relations on the S1 and S2, which force these 2 particular elliptic curves to have the same zeta function at S1 and at S2. Now, the funny thing that happens is some of these relations are very special. You get the same relation on S1 and S2 that shows up for 3 choices of which elliptic curve you look at. So basically, you're getting 3 zeta functions being equal for the price of 1. Once you realize this is happening, you go back to the drawing board and you say, well, if I have one of these special relations, how many pairs of curves, in other words, choices of the parameters S1 and S2, satisfy that relation? Well, that's a constant times p of them. If you have that relation, you get 3 zeta functions out of these 6 being equal already. And then to get a doubly isogynous pair, you just need 3 more zeta functions of elliptic curves to be equivalent by chance. That coincidence happens with probability a constant over the square root of p to the 3rd power. And so overall, you therefore expect a constant over the square root of p doubly isogynous pairs. That's really good. We go back and look at what we were seeing experimentally. If we increase n by 2, we're going to roughly quadruple the size of the primes we're looking at that are close to 2 to the n. And that should have the number of doubly isogynous pairs. And that's exactly what we're seeing. So we're really happy. We've really understood enough about the geometry of the situation to make a correct prediction that matches up with what we're seeing. So in particular, the default prediction was wrong. And so we really had to understand this sort of more complicated behavior to figure out what's going on. And this is really important if you want to pursue an application to factoring. I just want to leave now with some further questions, which are good questions for future research. The first one is, well, if you want to use this for this idea for factoring, you really don't want to have curves which are doubly isogynous. So you want to get different zeta functions. And so you should really figure out really understand why these examples seem to have more doubly isogynous pairs than you were expecting, and make sure that doesn't happen. So we were finding these special relationships, and the question is, can we systematically find them? And in particular, can we rule them out? If you want to use a family of curves in factoring, you better use a family where you can rule them out. And so Felipe Volek and I have been thinking about this, and we have an approach of how to do this using differential algebra, some ideas of Bayum. And what this would do is, if I give you a family of curves, it would turn finding all these special relationships into a question of just, you translate it into a question about solving a system of differential equations over the rational numbers. So that would be a very good thing to start with. Now, another question you really should worry about is this sort of randomness heuristic supported in other cases? So the cases I looked at today, the zeta functions broke up into lots of simple pieces. You just got zeta functions of elliptic curves instead of zeta functions of homogeneous curves, which weren't breaking up. And that is because our family had lots of extra automorphisms. And so is this random heuristic supported in other cases? And that would be a problem that would be good to have an undergrad student work on, maybe someone trying to do a summer project or a senior thesis, because you can start just computationally seeing what's happening, and then you can go try to explain any anomalous behavior that's not quite in line with the sort of basic default randomness heuristic. And then, of course, you'd like to prove things. And so the question is, can you actually prove that this sort of heuristic is right? In particular, prove that in cases there are no collisions, no doubly isogynous curves. This is something that seems like it should be connected to a theory in algebraic geometry called the theory of unlikely intersections. Now, the problem is people usually only talk about this and study it over the complex numbers. There are only a few fragmentary results where people looked at this over finite fields. And so it would be a substantial project to actually develop this theory and then see if it can actually prove the kind of results we're interested in. In particular, if you could do it, you would actually maybe get this application to efficiently factoring polynomials. And investigating this, as I said, is a long-term project, and I'm surely would spawn various interesting questions for graduate students to look at. And finally, for reasons of time, today I was focusing on projective curves and unramified covers, which are the analog of covering spaces. But you can also ask similar questions for affine curves and branched covers. And Felipe Volek and I have also looked at this, and we've made some partial progress. For example, if I give you a plane curve, we can use L functions of various ramified covers to determine the equation of the plane curve. All right, so in the last minute or two, I just want to talk about how this fits in with my broader research program. I've been telling you really about a very sort of small part of my research, but it makes a very nice story. And broadly speaking, my research is all about sort of covers in various settings. So I've been telling you about covers of curves over finite fields, and this particular question about can you hear the shape of a curve. There are other related questions about covers, some related to looking at ZP towers and how this is a new version of geometric Iwasawa theory, and also various questions about constructing special covers of curves with nice properties and studying the moduli space of curves and characteristic P. And then there's a whole part of my research which I said nothing about, which is about looking at the analog of covers for number fields, which is looking at Galois extensions of number fields. In particular, I've been interested in looking at Galois representations. These are the sort of circle of ideas which grew out of Andrew Wells's proof of Fermat's theorem. And I'm looking at, in particular, the deformation theory of Galois representations. So this has connections with modular forms, the Langlands program, and p-adic Hodge theory. And I also am interested in working on those sorts of things. All right, so thank you very much for your attention. I hope I told you some useful things about what I'm interested in terms of research, and also told you a good story about can you hear the shape of a curve. Thanks. So I'm happy to answer questions. I have the chat open, and you can also unmute yourself and ask them.
I have a sort of a general question. You mentioned the name of this Japanese mathematician from Kyoto. I forgot, Mochizuki. Machizuki. All right. So anyway, so you referred to some aspect of his work, and of course he has made headlines because of the ABC picture and some really radically new ideas that he has introduced. The reason I bring this up is since you have association with Arizona, there's a young person there, Kirti Joshi or someone, who is trying to get alternate explanations of Machizuki's methods. And since you did mention last theorem and other things, and and ABC is not too far away from that, are there potential connections or things that you'll be doing in relation to these very new techniques that are coming out of Machizuki's paper, whether or not the ABC conjecture is resolved?
Yeah,
definitely very new ideas.
Yeah, so not directly. The results of Machizuki I mentioned was some of his previous work, which is really sort of what built his representation. So everyone took it very seriously when he announced his proof of ABC. So in terms of Kirti's work, he's really more interested in looking at situations that are sort of a little bit different. Like I'm really focused on looking at curves over finite fields for this problem. So there's no direct sort of connection in the techniques. I was at the University of Arizona, so I talked with Kirti a little bit, and I'm looking at his recent preprints. Nothing in there immediately strikes me as being relevant, but it's really nice to see people trying to take these ideas and explain them in other ways that other people will hopefully understand, and maybe someday there will be ideas which match up nicely.
Thanks.
Other questions? I see Vince is busy. Other questions? Comments?
Can you explain in a few words what the special condition was that you referred to a few times?
Yeah, let's see. So when you're asking for these zeta functions of various of the elliptic curves showing up, what you're really doing is you're saying, I have these two elliptic curves, and I want to find a degree and isogeny between them. And that's what so there's a modular polynomial, and you compute the J invariance for these elliptic curves. You plug them into the modular polynomial, and you ask, is it 0? That's when they'll be an isogeny. That's when they'll have the same zeta function. And so that gives you a relation on S1 and S2. And you can change exactly which pair of curves you look at, and you can also change the degree of the isogeny. And so as you start doing that, you just get a bunch of relations, and then seemingly by chance, although you can explain this geometrically, you get the same relationships over and over again. So there are various, you can ask like this, you can ask this question for three different of the elliptic curves which show up, and you get the same answer. And that's one of these special relationships I mentioned.
I see. So basically it's the map from your base space to the modular curve. In some sense, it's the fibers that map. Yeah,
so you can interpret it also as like a sort of a family of isogenies between your sort of family over some special subspace of the sort of like your parameter space A1 times A1 or something.
Okay.
Yeah, so I have a question. So your first guess, on your heuristic, which turned out to be wrong, because of these unexpected relations, is that related in some way to the fact that you're looking at a family of curves that had more automorphisms than these, these hyperelliptic curves would normally have?
It's more than just that. So it's a little hard to give a precise answer to that question, because what I haven't done is done the sort of follow-up project about looking at a family without extra automorphisms carefully. But somehow what I have done is looked at an example. Well, it's not as carefully, but I have looked at an example where you just compute a bunch of zeta functions for a higher genus family. And for one of those examples, we found a lot more collisions than sort of an initial guess was. For another one, we didn't. And I don't know why that was happening yet, because I haven't fully analyzed that situation. But these were situations where we didn't have these extra automorphisms, which were causing the zeta functions to break up into simple pieces. So I think it's not just breaking up, it's really, there can be things which take whatever size pieces you have and cause them to somehow collide unexpectedly. And the sort of mysterious thing is exactly why is that happening and how can you rule it out?
So I guess the answer to my question is no, the automorphisms are not sufficient to explain this.
Yeah, but I wouldn't be quite that bold, because I think like they are playing some role in, I wouldn't be quite that bold, because I think it might be even more complicated than I'm imagining right now.
Yeah, I guess I used the word related, and so I guess that,
Okay.
that covers.
I guess that's, then I can say no with that weasel word.
Thank you.
Any other comments, questions, anything? So
hi.
Go ahead.
Sorry. Not a question, but I just want to say hi to Jeremy. That when we were in Arizona in 2017, I was in Jeremy's number theory class. if you remember, I finished my bachelor at that time, and I was auditing your number theory class.
You were interested in logic?
Yes, yes, that's me.
Yeah.
And I came to Florida doing logic, and I almost done with my PhD.
Congratulations.
I just submitted my paper, yes, last week, and now I'm looking for postdoc.
Okay, it's great.
And yeah, I was a student of Dr. Case.
Oh, nice to see you.
So good. Yeah, nice to see your talk.
Yeah, and I finally found your picture in the Zoom window by scrolling. So good to actually see you.
Yeah, I didn't even read your name of this talk. I just came and realized that you look familiar.
Okay.
And I looked up your CV and made sure that you are the person I thought.
Yeah.
So any